Welcome to Eternal Vault. Today, we journey into humanity's two greatest frontiers, the crushing depths of the ocean and the boundless void of space. For centuries, we've looked to the stars, building telescopes and rockets to chase distant worlds, while beneath us lies an alien realm of trenches, towering mountains, and life without sunlight. This essay explores both domains, the mysteries, the technology, the life, and the philosophy, revealing how oceans and space, though different, mirror our endless curiosity and push the limits of human imagination. The deep ocean is often called the last unexplored frontier on Earth, yet it is closer to us than any star. Beginning at around 200 meters below the surface, this realm descends into perpetual darkness. Sunlight does not penetrate here, leaving the world in an eternal twilightless void. The deep sea accounts for more than 90% of the planet's habitable volume, yet scientists have only touched a tiny fraction of it. Unlike deserts, forests, or even polar regions, the deep ocean is completely alien to the human eye, an environment we can only experience through sophisticated instruments or the brief presence of a submersible. Life in the deep sea is astonishingly diverse and often defies the conventional rules of biology. Biologists have discovered entire ecosystems centered on chemical energy rather than sunlight. Hydrothermal vent communities, first discovered in 1977, feature organisms like tube worms that rely on internal symbiotic bacteria to convert chemicals into energy, bypassing photosynthesis entirely. Equally remarkable are cold seeps, where methane or hydrogen sulfide support specialized microbial life and their predators. Some microbial colonies live within the rock and sediment itself, forming a biosphere that extends kilometers beneath the ocean floor. This deep biosphere may rival the total biomass of surface life, challenging our definitions of habitable environments. Geologically, the deep ocean is as dynamic and dramatic as the most alien landscapes in space. The mid-ocean ridge, a continuous undersea mountain chain longer than 65,000 kilometers, produces new crust as tectonic plates diverge. Massive submarine volcanoes create islands and reshape seafloor landscapes. Giant underwater landslides, known as turbidity currents, move enormous volumes of sediment, carving submarine canyons and reshaping the continental margins. The Mariana Trench, reaching nearly 11 kilometers deep, contains pressures exceeding 1,000 atmospheres, equivalent to the weight of several hundred cars stacked on a single human body. Under such forces, even the hardest metals deform, and only specially engineered spheres or shells allow human-built instruments to survive. Temperature gradients in the deep ocean are extreme. Near hydrothermal vents, water can reach over 400 degrees Celsius, yet just a few meters away it drops to near freezing. This sudden contrast creates a highly corrosive environment that challenges the durability of instruments and vehicles. Pressure and temperature also influence chemical reactions, making the deep ocean a laboratory for understanding geochemical processes that may have shaped life on Earth billions of years ago. From an exploratory perspective, mapping and documenting the seafloor is slow and painstaking. Satellites can measure the ocean surface and infer seafloor features through gravity anomalies, but high-resolution sonar mapping is still incomplete. Projects like Seabed 2030 aim to map the entire ocean floor, yet even with decades of effort, progress is gradual due to the logistical challenges of deep-sea expeditions. Robots like autonomous underwater vehicles, AUVs, and remotely operated vehicles, ROVs, extend our reach, but energy limitations, communication delays, and mechanical constraints restrict their capabilities. The deep sea also holds historical and cultural mysteries. Ancient shipwrecks, from Roman vessels to sunken fleets of World War II, lie in cold, oxygen-poor layers of sediment, often preserved better than in any museum. Biologists and archaeologists alike view these sites as time capsules, offering insight into human history and Earth's past ecosystems. Some speculate that undiscovered biological or biochemical compounds in these hidden worlds could hold medical or technological potential, as enzymes from extremophiles have already revolutionized industrial chemistry. If the deep sea is alien and extreme, space is incomprehensibly vast. Beginning just 100 kilometers above Earth beyond the Kármán line, space extends to the observable universe, encompassing hundreds of billions of galaxies. Unlike the dense medium of water, space is a near-perfect vacuum, almost entirely devoid of matter. Yet this emptiness is filled with invisible forces, radiation, magnetic fields, and streams of charged particles from stars. Temperatures fluctuate between extremes, from near absolute zero in shadow to hundreds of degrees Celsius in direct sunlight. Exploration in space faces entirely different challenges than the deep sea. Distances are staggering. The Moon, a mere 384,000 kilometers away, took humanity 8 days to reach with the Apollo missions. Mars lies hundreds of millions of kilometers distant, requiring months of precise orbital navigation. The outer planets like Jupiter and Saturn are billions of kilometers away, and reaching them demands not only propulsion, but clever use of gravity, assists, and trajectory planning. Light itself imposes a limit. Signals from Mars take over 20 minutes to reach Earth, while Voyager 1's current signal takes more than 22 hours. Radiation is a constant threat. Solar flares and cosmic rays bombard spacecraft and astronauts alike. Electronics degrade, human DNA is damaged, and long-term missions face cumulative risks. Thermal extremes necessitate highly sophisticated insulation, radiators, and heat control. Even micrometeoroids traveling at orbital velocities can pierce spacecraft hulls, endangering both robotic and human explorers. Space exploration has revealed astonishing discoveries. Telescopes like Hubble and James Webb peer back billions of years, revealing early galaxies and potential planets for habitability. Moons such as Europa, Enceladus, and Titan are now known to host subsurface oceans or organic-rich environments, suggesting that life may exist beyond Earth. Missions like the Europa Clipper or Dragonfly to Titan represent the next frontier, using robotic instruments to probe alien worlds we cannot yet physically inhabit. Philosophically, space reminds us of our smallness and connectedness. The overview effect, experienced by astronauts, describes a profound shift in perspective when seeing Earth from orbit. The planet appears fragile, beautiful, and unified, floating in a vast cosmic arena. This perspective mirrors the wonder inspired by the deep ocean, which, despite being on our home planet, also evokes awe and humility at the complexity and scale of life. Despite their differences, the deep sea and space exploration share technological ancestry. Pressurized capsules pioneered by Auguste Piccard in the mid-20th century were used for both high-altitude balloon flights and deep-sea submersibles. Both domains require a bubble of survivability, a controlled environment maintaining life support under extremes. Deep-sea engineering has inspired extraterrestrial mission design. AUVs built to navigate unmapped trenches inform the creation of autonomous probes for icy moons. Thermal management, corrosion resistance, and energy storage in submersibles guide engineers when designing spacecraft to survive extreme radiation, cold, and vacuum. Conversely, space-grade sensors, cameras, and communications equipment have found use in oceanographic instruments, increasing sensitivity and reliability under pressure. Funding and public interest remain uneven. Space exploration has historically received massive investments from nations like the United States, China, India, and the European Union. NASA, ESA, CNSA, and ISRO channel billions into telescopes, rovers, and orbital infrastructure. Deep-sea exploration, however, is largely underfunded, driven by specific goals like resource surveying, submarine cable placement, or scientific curiosity. NOAA's Office of Ocean Exploration operates on a fraction of the budget, yet its work could hold answers to climate change, biochemistry, and even medicine. Life is the most compelling link between the oceans and space. Extremophiles in the abyss provide a blueprint for potential life elsewhere. Microbes thriving in freezing, high-pressure, oxygen-poor conditions suggest that Europa's subsurface ocean or Enceladus's geysers could host life. Bioluminescence in deep-sea organisms shows how communication, predation, and mating can evolve under absolute darkness, a model for understanding how alien life might function under icy crusts or deep oceans on exoplanets. The discovery of chemosynthetic ecosystems demonstrates that life does not require sunlight, expanding the criteria for habitable worlds. Astrobiology increasingly relies on oceanic analogs. NASA's training in deep ocean habitats like Aquarius Reef Base allows astronauts to practice techniques for exploring icy moons. Instrumentation developed for hydrothermal vent studies helps design probes for analyzing extraterrestrial water chemistry. Understanding the deep sea is in many ways a prerequisite for understanding life in space. Both realms challenge human perception and humility. The deep sea represents a reminder that Earth is still largely unknown, while space challenges us with scale, time, and relativity. Literature, art, and myth reflect these fears and fascinations. The Kraken symbolizes the terror of unknown waters, while celestial myths describe humanity's longing for stars. Science fiction often merges the two, imagining alien oceans on distant worlds or deep-sea civilizations under the ice of Europa. Exploring these extremes teaches resilience. The patience required to map the seafloor mirrors the long-term planning of interplanetary missions. The engineering solutions, pressure-resistant hulls or radiation-shielded spacecraft, show ingenuity in confronting inhospitable environments. Both frontiers remind us that exploration is not merely about discovery, but about testing the limits of human creativity, endurance, and understanding. Humanity's fascination with extremes dates back millennia. Ancient civilizations revered the seas and the stars, often intertwining their myths. Mariners of the Indian Ocean from the Indus Valley to the Chola Empire navigated by the stars, showing early recognition of celestial patterns for survival. Likewise, early Greeks personified the ocean in deities like Poseidon, linking reverence with fear of the unknown. The Polynesians, centuries before Europeans, charted the vast Pacific using intricate knowledge of currents, winds, and stars, demonstrating that early humans could master seemingly insurmountable environments both on Earth and in the sky. In more modern history, the race to explore the deep ocean began in earnest during the 19th century. Pioneers like Sir John Murray and the HMS Challenger expedition, 1872-1876, laid the groundwork for modern oceanography. Using rudimentary sounding lines and dredging equipment, they documented the first systematic profiles of the seafloor, discovering thousands of previously unknown species. Meanwhile, the 20th century saw a parallel surge in space exploration, beginning with rocketry and culminating in the space race between the USA and USSR. Each frontier was, in its own way, a testament to human ambition and ingenuity. Countries across the globe have contributed uniquely to these dual explorations. The USA invested heavily in space with NASA, producing landmark achievements like the Apollo moon missions, Mars rovers, and the Hubble Space Telescope. Deep-sea exploration also flourished, with NOAA and private institutions deploying advanced submersibles. China, meanwhile, has emerged as a leader in both realms. The Chang'e lunar missions, the Tiangong space station, and robotic deep-sea submersibles like the Jiaolong highlight dual investment in extreme frontiers. India's contribution, though smaller in scale, is significant. The Chandrayaan and Mangalyaan missions demonstrated the nation's ability to explore lunar and Martian terrains efficiently, while its deep-sea programs monitor the Indian Ocean's geophysics and biodiversity. Europe, through ESA, maintains a strong presence in space, contributing telescopes, satellites, and robotic explorers, while deep-sea research vessels like France's Pourquoi Pas and Germany's Meteor advance oceanographic mapping. Russia, with a long history of both Arctic and deep-sea research, continues to deploy submersibles alongside its space initiatives, highlighting centuries of dual frontier expertise. The deep ocean is defined not only by pressure and darkness, but also by chemical extremes. Hydrothermal vent communities rely on chemosynthesis, a biological process that converts chemical energy into biomass, bypassing sunlight entirely. Organisms like Riftia tubeworms host symbiotic bacteria capable of converting hydrogen sulfide into nutrients, creating complex ecosystems invisible from the surface. Some microbes survive in oxygen-deprived sediments, metabolizing methane, iron, or ammonia. These extremophiles provide insights into the limits of life, suggesting that habitability is not constrained by temperature, pressure, or light alone. In space, extremophiles serve as models for potential extraterrestrial life. Tardigrades, for example, survive vacuum, extreme radiation, and sub-zero temperatures. Studying their DNA repair mechanisms helps astrobiologists understand how life could endure on Europa, Enceladus, or even Mars. Experiments on the ISS have exposed microbes to cosmic radiation and microgravity, revealing adaptation strategies that mirror survival tactics in deep-sea vents. This connection emphasizes a profound truth. Earth's extremes are laboratories for understanding life beyond our planet. Chemical conditions in both realms reveal astonishing parallels. Hydrothermal vents release mineral-rich fluids at hundreds of degrees Celsius, creating sharp thermal and chemical gradients. These environments host unique enzymatic reactions, sometimes occurring in silica or iron-rich matrices that stabilize otherwise fragile molecules. These same principles guide our search for extraterrestrial biosignatures. For instance, the geysers of Enceladus eject water rich in salts and organic compounds, analogous to deep-sea vents on Earth. By analyzing the chemistry of these plumes, missions can detect potential metabolic byproducts or amino acids that signal life. In the deep ocean, manganese nodules, polymetallic sulfides, and rare earth deposits reveal Earth's geochemical richness. The formation of these structures, often over millions of years, mirrors processes in planetary crusts elsewhere. By understanding deep-sea mineralogy, scientists gain insights into planetary differentiation, tectonic activity, and the potential for mining or resource utilization beyond Earth. Humanity's ingenuity is showcased in engineering feats for both realms. The DSV limiting factor, capable of repeated dives to the Mariana Trench, exemplifies modern materials science, pressure resistance, and life support innovation. Tethered ROVs, equipped with high-definition cameras, manipulator arms, and multi-beam sonar, allow exploration of hydrothermal fields, deep coral reefs, and methane seeps. Spacecraft like the James Webb Space Telescope and Voyager 2 push engineering boundaries differently. JWST's deployable sunshield, cryogenic instruments, and gold-coated mirrors demonstrate mastery over thermal control, optics, and vacuum compatibility. Voyager 2, traveling beyond the heliosphere, continues to transmit data from billions of kilometers away, a testament to long-term autonomy, power efficiency, and communication engineering. Interestingly, cross-pollination occurs between the two fields. Pressure-resistant housings, corrosion-resistant materials, and autonomous navigation software developed for deep-sea vehicles have informed robotic planetary probes. Conversely, radiation-hardened electronics, solar power management, and autonomous hazard avoidance techniques from space missions enhance underwater exploration technologies. Exploring the deep sea requires overcoming depth and opacity. Radio waves are absorbed almost immediately underwater, necessitating acoustic communication systems. Sound travels about 1,500 meters per second in water, making high-resolution data transmission slow. Remote piloting of ROVs introduces latency, demanding predictive control algorithms. In space, distance is the primary challenge. Signals travel at the speed of light, introducing delays that range from minutes to hours depending on distance. Autonomous spacecraft must make decisions without real-time input. Mars rovers, for example, execute sequences of commands for hours while accounting for hazards, slope gradients, and dust accumulation. Interplanetary missions must consider orbital mechanics, gravitational assists, and energy-efficient trajectories, a logistical complexity unmatched in any terrestrial setting. Human culture has been shaped by both realms. Deep-sea myths, from the Kraken to the Leviathan, reflect humankind's awe of the unknown. Submersible expeditions inspired literature and visual media, from 20,000 Leagues Under the Sea to modern documentaries. Space exploration, similarly, fuels imagination, inspiring science fiction, philosophy, and international collaboration. Astronaut reflections often inspire global environmental consciousness, while planetary discoveries challenge religious and philosophical ideas about humanity's uniqueness. In modern media, comparisons between ocean and space exploration are frequent, highlighting parallels: isolation, extreme environments, and encounters with alien-like life. Films like The Abyss, Interstellar, and Gravity blend science and art to depict these extreme conditions, emphasizing human adaptability and curiosity. Both domains continue to promise revolutionary discoveries. Deep-sea bioprospecting may yield antibiotics, enzymes, and bioactive molecules for medicine and industry. Unexplored hydrothermal vents, Hadal trenches, and seamounts could host species with biochemical mechanisms unlike anything known. Space exploration may reveal life or habitable environments beyond Earth. Europa Clipper, Dragonfly, and the James Webb Telescope are poised to expand knowledge of exoplanets, moons, and distant galaxies. Artificial intelligence and autonomous robotics will play critical roles in both realms, handling navigation, data collection, and adaptive problem-solving where humans cannot reach. International collaboration is also key. Initiatives like the UN's Outer Space Treaty and Seabed 2030 illustrate the need for collective stewardship of unexplored frontiers. India's Gaganyaan mission, China's Chang lunar exploration, NASA's Artemis program, and Europe's exoplanet observatories exemplify global efforts converging on shared scientific goals. The history of deep-sea exploration is punctuated by landmark missions that redefined human understanding of the oceans. The bathyscaphe Trieste, designed by Auguste Piccard and piloted by Don Walsh and Jacques Piccard in 1960, became the first manned vessel to reach the Challenger Deep, the deepest known point in the Mariana Trench. At nearly 11 kilometers below sea level, the submersible endured pressures exceeding 1,000 atmospheres. The mission revealed a desolate, sediment-covered seafloor, seemingly devoid of life. Yet later expeditions showed that even in these extreme conditions, life thrives. Subsequent dives by the deep-sea Challenger and Limiting Factor documented shrimp-like amphipods, giant amoebas, and previously unknown microbial mats, confirming the resilience and adaptability of life. remote and autonomous vehicles have expanded the scope of deep-sea research. The ROV Jason and autonomous gliders like Sea Glider map vast regions of the seafloor, studying hydrothermal vents, underwater volcanoes and cold seeps. Japan's Shinkai 6500 explores depths exceeding 6,500 meters, capturing high-definition footage of previously uncharted species. These missions have uncovered biological adaptations like antifreeze proteins in Antarctic fish, hydrothermal vent chemosynthetic ecosystems, and microbial life capable of metabolizing toxic metals. Globally, nations are increasing investments in ocean exploration. China's Jiaolong submersible, which has reached 7,000 meters, demonstrates Beijing's commitment to marine science. India's Samudrayan project aims to send humans to 6,000 meters, expanding understanding of India's exclusive economic zone in the Indian Ocean. European nations maintain fleets of research vessels that conduct multi-year campaigns, combining sonar mapping, sediment analysis, and deep-sea sampling. These expeditions reveal not only geological and biological treasures, but also immense potential for resources and a deeper understanding of Earth's climate history, as sediment cores preserve climate records stretching back millions of years. In space, robotic missions have pushed human knowledge to staggering distances. The Voyager program, launched in 1977, has traveled beyond the heliosphere, transmitting data about the interstellar medium, solar wind, and cosmic rays. Voyager 1 and 2 have provided humanity's first in-situ measurements of the space between stars, revealing unexpected magnetic field interactions and the nature of galactic cosmic radiation. Closer to home, the Mars rovers, Spirit, Opportunity, Curiosity, and Perseverance, have revolutionized planetary geology. High-resolution imagery, rock and soil analysis, and the detection of past water signatures on Mars indicate the planet once hosted conditions suitable for life. The Ingenuity helicopter has demonstrated powered flight in a thin atmosphere, proving technologies previously thought impossible on other planets. The James Webb Space Telescope, launched in 2021, has expanded the observable universe by peering into the earliest stages of galaxy formation, detecting potential water vapor in exoplanet atmospheres, and identifying unusual cosmic structures like ultra-compact dwarf galaxies. NASA's Europa Clipper mission, slated for the late 2020s, exemplifies the intersection of oceanic and space science, using ice-penetrating radar and mass spectrometry to study a subsurface ocean that may harbor life. China's space program contributes significantly, with Chang'e lunar missions providing high-resolution topographic data, regolith samples, and evidence of water ice in permanently shadowed regions. India's Mangalyaan and Chandrayaan missions have demonstrated cost-effective space exploration, delivering high-quality data on Mars's atmospheric composition and the Moon's mineralogy. ESA's Solar Orbiter and ExoMars projects advance understanding of solar dynamics and planetary habitability. These missions highlight that, as with the deep sea, humanity's reach into space is a combination of robotic precursors, incremental technological innovation, and ambitious international collaboration. A striking similarity exists in the challenges of deep sea and space exploration. Both demand the creation of self-contained autonomous environments. Deep-sea submersibles require life support, pressure-resistant hulls, and precise navigation. Spacecraft demand radiation shielding, thermal control, and airtight environments. Both rely increasingly on autonomy to compensate for delays or communication limitations. Underwater navigation uses sonar, Doppler velocity logs, and inertial measurement units to map terrain invisible to the naked eye. Spacecraft use star trackers, gyroscopes, and gravitational models to traverse vacuum. Both environments challenge the limits of material science. Titanium ceramics and syntactic foams provide strength under high pressure, while carbon composites, aluminized polymers, and multi-layer insulation protect against vacuum and temperature extremes. Autonomy is key. In the deep ocean, vehicles must adjust buoyancy and avoid obstacles without constant human input. In space, probes like the Mars rovers navigate slopes, detect hazards, and optimize science collection autonomously. Artificial intelligence is bridging the two domains, enabling real-time decision-making where humans cannot intervene. In the coming decades, AI-driven autonomous exploration may become standard, whether probing a hydrothermal vent 8 kilometers deep, or analyzing a geyser plume on Enceladus millions of kilometers away. The drive to explore the unknown reflects fundamental aspects of human consciousness. Ancient myths linked the stars and seas to the divine, creating cosmologies that shaped morality, navigation, and society. Today, our exploration of extreme environments continues that tradition, blending science with existential curiosity. The deep sea reminds humanity of humility. Despite dominating land and air, Earth's oceans remain largely hidden and unexplored. Space provokes awe. Even with the Hubble and JWST, the universe's scale dwarfs our comprehension, highlighting our temporal and spatial insignificance. Moreover, exploration fosters cooperation and competition simultaneously. The Apollo missions were both geopolitical tools and scientific endeavors. Modern collaborations like the International Space Station, seabed 2030, and joint planetary missions emphasize global interdependence in extreme science. India, China, USA, Russia, and Europe each bring complementary expertise, and private initiatives, Blue Origin, SpaceX, Ocean Infinity, accelerate innovation. Ethical considerations arise too. Deep-sea mining, exploitation of genetic resources, or extraterrestrial sample collection demand international frameworks to balance discovery with preservation. Looking forward, the next decades promise unprecedented convergence between oceanic and space exploration. Advanced materials may enable submersibles to reach the Hadal Zone more efficiently, while robotic probes equipped with AI may navigate alien oceans or icy crusts. Swarms of autonomous drones could map seafloor ecosystems in high resolution, simultaneously testing technologies applicable to distant moons. Space missions may employ similar designs: ice-penetrating robots, miniature autonomous submarines, and self-repairing systems. Discoveries in the deep sea may guide life detection protocols in space, from chemical biosignatures to mechanical navigation techniques. The integration of oceanic and space technologies exemplifies humanity's ability to learn from extreme environments, turning Earth into a testbed for the cosmos. The discovery of extremophiles on Earth has reshaped biology and astrobiology. Organisms thriving in acidic vents, near superheated fluids, or anoxic sediments demonstrate that life is not confined to mild sunlit environments. Analogous conditions exist on Europa, Enceladus, and potentially Titan, where liquid water, chemical gradients, and internal heat may allow life to emerge independently. Scientists are increasingly studying deep-sea microbes, their DNA repair mechanisms, and metabolic pathways to hypothesize life on other worlds. The study of bioluminescence, symbiotic bacteria, and pressure-adapted physiology informs the design of instruments to detect life remotely. Planetary protection protocols also mirror oceanic ethical considerations. Contamination must be avoided to preserve the natural state of extraterrestrial ecosystems. The fusion of knowledge from oceanography and astronomy underscores a larger trend. Extreme environments are laboratories for interdisciplinary science. Deep-sea geophysics informs planetary geology. Hydrothermal vent chemistry mirrors extraterrestrial chemical systems. Robotics, AI, materials science, and life sciences converge in both domains, pushing the limits of engineering, autonomy, and biological understanding. International collaboration will continue to define future success. Shared databases, open-source mapping projects, and joint missions expand capabilities beyond what any single nation can achieve. Projects like seabed 2030, the JWST observations, and the Europa Clipper mission exemplify this new era of collective exploration. Ultimately, the deep ocean and outer space are two sides of the same human drive, to confront the unknown. The oceans, dense, dark, and dynamic, challenge us to engineer resilience and adaptability. Space, vast, radiant, and empty, challenges our imagination and endurance. Both realms demand technological innovation, courage, patience, and philosophical reflection. We must continue to explore both simultaneously. Understanding Earth's hidden oceans prepares us for the discovery of alien oceans. Probing distant stars inspires new oceanic technologies. Exploration is not just a scientific endeavor, it is a moral and cultural mission, reminding humanity of its interconnectedness with the universe and its responsibility to steward both Earth and space wisely. Whether drawn to the crushing darkness of the Mariana Trench or the infinite void of space, the frontier calls. Our species thrives on curiosity, resilience, and the desire to reach beyond limits. Each discovery, every unknown species, every distant exoplanet, every unmapped trench or crater, is a testament to human ingenuity and the eternal quest to understand life, Earth, and the cosmos. The frontier is endless, and humanity is only beginning to grasp its magnitude. For some, the alien life beneath the waves is the ultimate mystery. For others, it is the search for life among the stars. Both are essential, complementary, and humbling. They define our species' greatest pursuit: to know, to explore, and to see what lies beyond the next horizon. Conclusion: two frontiers, one human drive. Ultimately, the deep sea and outer space are not competing domains, they are complementary. One urges us to look inward, understanding the hidden alien world beneath our oceans. The other pushes us outward, stretching our vision to distant stars, moons, and galaxies. Both expand our understanding of life, physics, and the limits of possibility. The technologies, philosophies, and discoveries in one often illuminate the other. Submersibles inform probes, and telescopes inspire mapping techniques. Extremophiles in the abyss guide the search for extraterrestrial life. The human spirit is the true frontier, driven by curiosity and courage, whether diving into crushing darkness or reaching toward infinite voids. So, which mystery captivates you more, the uncharted worlds beneath our oceans or the endless expanses above? In truth, the exploration of both is essential, and together they define the limits of human knowledge, ambition, and imagination.